try to impart what we always strive to be useful information and delivered in an unbiased way, so as to address the educational perspective as opposed to a sales indoctrination perspective. Today, you see from the title and saw in the advanced summary, which you found on our website or our e-blast, a first of a two-part series on boiler system chemical treatment, an area which may view as a mystery, not really understanding what the chemicals used are, and really more importantly, the how and why of their use, to say nothing about the real importance of diligently following the routines associated with their use. So we hope to begin dispelling the mystery and complacency surrounding chemical control of boil water and feed water by addressing the subject in layman terms, devoid of the formulas, combination chains, and complexities normally associated with this subject. In other words, Bill and I want to make it real. As you heard, assisting me today is Bill Hook, the National Chemtex Corporation, who is with them. Will be presenting really the real meat for today's session after I set the stage, so to speak, with some comments in order to properly focus and set his commentary up. So here's today's agenda. First of all, we're going to be looking at a 35,000-foot view of a sound water treatment program. And this will be something that you've heard before, but good view quickly again. And highlights from last month's chemical dosing webinar. Those of you who either tuned in live or looked at it on our website, just highlight some of the important issues that were discovered or were discussed last month. And then a quick overview of hot water systems. Bill is going to be talking about chemically treating those as well. Then the key water treatment problems facing steam supply systems will be looked at, and then, of course, acting on those or attacking those particular problems. Then about the problems with the condensate piping and its remedies. And then hot water system treatment and good record keeping. Very, very important. So looking at the slide on the screen now, I think it really says it all. A water treatment program is really a two-part deal wherein both the mechanical and the chemical remediation required and working in tandem. First, to mitigate operational costs while assuring the boiler and the associated systems remain reliably operating. They're not wasting valuable energy, and of course we remain safe. Yes, we often don't think of the chemical treatment program playing a vital role in keeping not just the boiler, but all the connected piping and support systems in good shape and sound working order too. So therefore, I really like to use the human body as the analogy or the metaphor in this instance, where the chemicals that we put into the boiler, the feed tank, and piping are similar to the medications that we use to keep us human beings healthy. Those drugs which keep our arteries and veins free of harmful cholesterol, that would be the steam lines and the condensate lines. Drugs or vitamins that we take for our heart and the boiler to sound working. In other words, when we take medications for health, it's not just for one organ. It's for general health of the entire system because they all work together. And to disregard any one component will cause the whole system to eventually fail. And what it is for a viable water treatment program. It's so important that we are of the problem areas which need to be controlled in order for our boiler system to remain healthy and sound. We doggedly control the hardness in the water, the total dissolved solids, and of course, the very damaging dissolved gases. Because if we don't, it won't be long in the boiler tubes and the connected piping will look like this. Or where a scale formed, causing the boiler tubes to overly extend because of overheating, breaking the welds at the tube sheet, and causing extensive leaking, downtime, considerable repair costs, and some production losses too. So, to stop this from happening, it's important that you engage the services of a good doctor, local treatment consultant, who understands your particular system and is willing to spend the time and the energy to prescribe the right type and amount of chemicals to assure your system performs at its peak all the time. Now, next, in part 2 of our 2-part series with Chemtechs, this is one of the subjects that we'll be covering, of choosing a reputable water treatment consultant that is right for you and your particular situation. So make sure you tune in again next month, and we've got it scheduled for November 30th, after Thanksgiving. And what about water consulting services? A big part of what this consultant will be recommending or possibly providing is the right dosing pump to dispense the chemicals he or she recommends at the proper levels and in the proper place, while also considering if the chemicals to be injected call for a special internal material within the wetted portion of the pump to damaging it. We discussed last month when we covered chemical dosing pumps in some detail. The sections are varied but can be broken down into 2 basic types. We have the hydraulic on the left and mechanical one, which you see on the right. And mechanical is also the one which is most often supplied in both applications, as it provides adequate pressure tolerance and also suction lift when the pump is placed on the top of the chemical tank. Placing the pump on top of the tank is used to conserve cost, but there is another option. That is a pre-engineered packaged dosing system. These can be a bona fide consideration in some applications because even though they are more costly, more expensive, they provide some distinct advantages. First, here all components are functioning properly as an integrated system. The systems normally involve 2 pumps to break backup should one fail, and thirdly, they easily integrated into a building management system. And fourthly, knowing that chemicals are a major operational cost, these systems are designed to assure optimum performance and precise metering of these chemicals to reduce ongoing costs. So it's certainly something to discuss with your water treatment consultant. And the other question often asked about dosing pumps, beyond the type selections I just reviewed briefly, is do you size one? And for those of you who attended last month's session or watched the playback from our Cleaver-Brooks website, sizing these chemical dosing pumps is not the same as sizing a centrifugal pump they use for boiler feed water. Required flow, the discharge head, and the required NPSH, net positive suction head, are precisely targeted. Because in the case of a chemical dosing pump, we really only consider pressure and flow, wherein the chart on the screen now depicts this particular dosing pump can operate anywhere within the bold lines encompassing capacity on the lower horizontal and the discharge pressure on vertical axis. From last month's webinar, the chemical dosing pumps are highly accurate and can deliver a wide range of flows as you see on the screen. And to put things in perspective, a pump can be selected for a flow equal to a teaspoon, or a pump can be selected for flows equaling the 3 drums shown on the right. It's all a matter of the problem to be solved and the right chemical and dosing quantity to solve it. Now, leaving the subject of chemical dosing pump highlights from last month, it would be good to say just a few words about some key points or tips to keep in mind. Is to make sure you have a straight line of pipe or tubing going into the chemical tank with a foot valve mounted at the bottom of the suction line so the pump can maintain its prime. That's what the foot valve does. This is to avoid cavitation problems, especially if you keep your suction line as short as possible. Now, an important tip to keep in mind is keeping the lift on the suction side of the pump within the recommendations of the manufacturer. to avoid any loops in the suction line, as shown in the picture on the right. This mistake will cause air to entrain in the line, thereby keeping the chemical from moving. Essentially, what we're talking about here would be very similar to a vapor lock. And lastly, it is recommended that you use a rigid suction line rather than a flexible one, and some clearance from the foot valve to the bottom of the tank to avoid sucking up sediment and other debris, which could cause check valves to fail and then the pumping to stop. So that's all I really had on the key reminders for chemical dosing pumps. Now, before turning the program over to Bill Hook, I just wanted to say a few words about hot water systems, as he is going to be discussing them from a chemical treatment perspective in just a couple minutes. You may or may not know, hot water piping systems have gone through many design changes over the years as comfort heating systems evolved from low-pressure steam to hot water, and designs also evolved to better accommodate the demands associated with demands for increased efficiency, shock protection, and the condensing of corrosive flue gases to get more energy taken from that flue gas, putting it into the boiler water to increase our overall efficiency. So in the interest of time, I'm going to quickly cut to the chase and just show you two most popular systems that are used today, and they are the primary-secondary piping system and the variable flow primary system. We'll look first at the primary-secondary system. You have two independent loops with their own set of pumps. The primary loop is for the boiler or boilers. The secondary loop is for the heating system. The reason for the primary loop is to make sure the boilers have adequate flow. In the case of boilers being non-condensing type, receive high enough return water temperatures so as to keep the flue gases from condensing. Remember, they're non-condensing boilers in this case. And the three-way valve is there primarily. It's used to adjust the system water temperatures on the secondary side based on the outdoor temperature demand as it varies up or down. System with the variable flow primary system, which is gaining considerable popularity today because of its simplicity and associated first cost and operational savings. In this system, you see the primary loop piping is eliminated, and primary pumps, which have been replaced with automatic isolation valves when the boiler is not firing or is not online. On the secondary side, you find the pumps have been equipped with variable speed drives, which of course saves electrical energy. Now, I mentioned before that not only have the piping systems been evolving over the years, but also the boilers have been changing to allow for much higher efficiencies and resistance to thermal stresses and fireside corrosion. Looking at the top piping arrangement, you see the primary-secondary system again with low mass condensing boilers delivering, depending upon the operational conditions, efficiencies in the very high 80s to 90s. These boilers need to be piped in the primary-secondary configuration due to the need for minimum flow because of their very low water mass. On the diagram, you find a variable flow primary arrangement with high mass condensing boilers. Now, this boiler is the only one that can be used in this piping arrangement as they have sufficient water mass to withstand minimum to no flow through them. And because of this, other facts, they always deliver efficiencies in the mid to high 90s, in addition to the electrical savings derived from the lack of primary pumping and, of course, the use of VFDs on the secondary side of the system. This is what we've seen today in regard to hot water piping arrangements commonly found in commercial and industrial heating applications. Another talking about the preliminaries for today's webinar. It's time to turn the program over to my associate for today's discussion on chemical water treatment for boilers and systems, Bill. Bill?
Good afternoon, Steve, and thank you very much for the kind words in the introduction. I really feel privileged to be here, and I like your analogy to comparing a boiler system to a body where a water treatment program might protect the entire system, and how that's key, because if you ignore one part of a system, it can negatively affect other parts of that system. So it's a good analogy. And what I'd like to do is remind everybody that this is going to be a very basic water treatment overview, and I'm going to be looking at the system from 35,000 feet, as you say. It's a general view, and we're not going to be talking specific polymers, and we might not be talking specifically enough for lists that you might be interested in. But when you do this, I hope that you're better off than you were in terms of understanding the program that we're talking about. So water treatment program is designed to minimize scale, corrosion, and it's designed to minimize carryover, which we're going to talk about next month. As a mere definition and a visual overview, this is scale. This is where there's a buildup of minerals on boiler tubes or piping. This is a photograph of some oxygen pitting on a tube inside of a fire tube boiler. A photograph of some condensate corrosion, which is very common and needs to be very strongly considered. And you can see the water runs through the bottom of a condensate pipe, and if left untreated, it can actually form a groove in the bottom of that condensate pipe, as you see in the photograph on the right. So, an allusion to this also, talking about the mechanical means that are used outside the boiler to remove components that form scale in the boilers. And that those components, mechanical components on the outside include water softeners, dealkalizers, and reverse osmosis equipment is becoming more popular now as its efficiency and cost has come down considerably. Mechanical means outside the boiler, which is absolutely critical, is minimizing the amount of oxygen that's going into a boiler system. And a deaerator has been talked about before, but a deaerator heats the water, it removes the dissolved oxygen and free carbon dioxide from the system, venting them to the atmosphere so that they're not entering into the boiler system. So inside the boiler, chemicals are used to prevent scale, and we're going to talk a little bit about that in a minute. As last month from the seminar, we talked about the tolerances that are recommended as guidelines by ASME to the water entering a boiler and the water that's inside a boiler. And ASME has defined the guidelines as this. I see clearly that you're talking about 0.007 parts per million of dissolved oxygen is all that should be allowed in the feed water entering a boiler. Total hardness should never be more than 0.3 parts per million. The feed water pH should be in the range of 8.3 to 10.0. And inside the boiler, ASME guidelines have changed over the years, and they now permit specific conductivity in a boiler to be 7,000, total alkalinity at 700, silica 150, and OH alkalinity generally 200 to 400 ppm, depending upon the pressure of the boilers. First, we're going to talk about corrosion and preventing corrosion in the boiler system, the boiler, and in condensate systems. Then we'll talk about preventing scale in the boiler. We're going to talk about a boiler water chemistry that allows for the efficient production of clean, dry steam. Go back and look again. This is an oxygen pit on a tube boiler. And what it looks like a little volcano, and if you scrape it off, scrape the metal off the top of that volcano, you'll be able to see that there's a pit underneath there. If there's oxygen in the boiler water and you heat the boiler water up, the oxygen is driven out of solution. It'll roll to the top of the tube where it finds a low spot like under this volcano, and it concentrates, and you've got a very corrosive atmosphere. This is a picture of oxygen corrosion in a water tube boiler where you can see oxygen on the steam separator. And in fact, on this boiler, this occurred when a boiler sat idle for a period of time after maybe 10 months of proper protection. It's idle for 2 months without proper sulfite, and it was able to, it coated while it was sitting idle in standby. Again, this is another photograph of a tube boiler and the corrosion that takes place in it as a result of oxygen corrosion, either insufficient sulfite during the operating time or insufficient sulfite during a standby period. Going to the ASME guidelines, there's, even with a dehydrator, there's a small amount of oxygen that enters a boiler even with a mechanical pretreatment. Oxygen scavengers are used to tie up the oxygen to prevent oxygen attack. And I'm going to say this next thing about 3 or 4 times during this presentation. The number cause of boiler tube failure is oxygen corrosion. So preventing oxygen corrosion is paramount part of any effective water treatment program. Chemical control in boilers is oftentimes done with sodium sulfite. It's with oxygen to form a harmless salt, and there are other oxygen scavengers that are used in the marketplace, but for the most part, sodium sulfite is the oxygen scavenger of choice. It happens inside the boiler when you're feeding sulfites. The sulfite, SO3, reacts with the oxygen that enters the boiler, and what that becomes is sulfate. And sulfate is a water-soluble salt, which with solution and can be removed through surface blowdown or through bottle blowdown. Another thing to remember is it takes 10 parts per million of sulfite to take up 1 part per million of oxygen that enters the boiler. Again, I mention this again, oxygen corrosion is the #1 cause of boiler tube failure, so maintaining a sulfite residual is a critical part to protection. Where fed, sulfite is fed as a liquid to either the storage section of the deaerator or to the feed water tank or to the feed water line, depending upon the specific system. Ideal circumstance, you're feeding sulfite with your dosing pump to the storage section of the deaerator. If you are feeding sulfite to a system where there is no deaerator and you're feeding it to a feed water tank, be careful not to feed your sulfite with your sulfite dosing pump into the air above the water level in your feed water tank. If you feed sulfite this way, you're to take the oxygen out of the air that's above water level in that feed water tank. You want to be certain if you're feeding to the feed water tank, you feed beneath the water surface so that you can scavenge the oxygen out of the water in the feed water tank before it goes in the boiler. How do you need to provide cushion to protect against oxygen corrosion? In most circumstances, 20 to 60 parts per million are the residuals that should be in a boiler to protect it against oxygen corrosion. Standby boilers might demand higher levels, but in most cases, 20 to 60 parts per million of sulfite is required to protect the boiler against oxygen corrosion. Sulfite demand. If there is a large demand for sulfite and you're adding large amounts of sulfite to the boiler, it will add conductivity to the boiler. This results in demand for extra blowdown. So what happens is you add more sulfite to the boiler, which increases your blowdown. You increase the blowdown, you add more makeup. When you add more makeup, the demand for sulfite goes up. And this is called the sulfite chase. And if this is occurring, strongly review your operation. Look at the limits and the controls that you've got to minimize this sulfite chase. It's very common in circumstances where we've got a small boiler with cool or cold feed water going into the boiler. Another couple of drawings that I'm trying to share with you to to talk about oxygen demands and the idea that sulfite takes 10 parts per million of sulfite for each 1 ppm of oxygen entering the boiler is the drawing on the left. You can see that if I've got feed water temperature 180 degrees, it's going to have roughly 3.5 ppm of dissolved oxygen in that feed water, which means it's going to demand 35 parts per million sulfite to tie that dissolved oxygen up. If I let the water heated to 205 degrees, I'm going to have to feed enough light to overcome 1 part per million dissolved oxygen. I'm only going to have to feed 10 parts per million of sulfite to overcome that oxygen demand. And on the right-hand side, I've put a chart together which depicts the cost of treating to chemically deaerate feed water based on different temperatures and based on whether you're eating a sulfite powder or a sulfite liquid. And if you look at the chart, you can see when you get up around 210 or 212, 220 degrees where you've got a deaerator in place, the costs for sulfite are very minimal. If I'm feeding I'm feeding feed water to a boiler, 180 degrees, it can be extremely expensive to remove the oxygen in feed water, and you might want to consider different options for treating the feed water depending upon the temperature. So we've got oxygen corrosion removed from the system using sulfite. Now we're going to go on to talk about preventing scale in the boiler. And as you've probably seen drawings and are well aware that scale is a very good limiter of end flow. If I got scale on a boiler tube, it's going to cost me more energy to generate the same amount of steam, and you can get a 1/16 of an inch of scale can increase your fuel costs by up to 14%. So it's important to invest in a good water treatment program, which generally makes up a very, very small portion of the overall operating budget of a boiler. So let's talk about controlling scale and what a definition of scale is. And there's a definition of scale there, which is one to choose, but scale occurs when the solution equilibrium of the water is disturbed by pressure and temperature changes, dissolved gases, or incompatibility between the mixing of a water source and chemicals. Layman's terms, minerals in solution in a boiler that can no longer remain in solution and drop out as a deposit are called scale. And pre-treatment equipment, again, is very important. It's a very important of a water treatment program, and maintaining this pre-treatment equipment on the outside of the boiler is critical and important to any operation. What does it look like? We've hopefully not all seen scale, but perhaps we have. This is the inside of a water tube boiler with just a very light film scale on it. Here's a fire tube boiler with a little heavier scale on the left and heavy scale again on the right. This is a tool that we've used to help track the inside of a boiler. When you're inspecting a boiler, when you climb in it, identify the tubes that you're photographing while you're inspecting your boiler. You can use a welding cran in this particular boiler. This is rows up, 2 rows from the front on a boiler that's been inspected, and the boiler tube looks pretty good. Now, this particular boiler tube doesn't look so good, and this is what's happened when a water treatment program has been ignored. And what happens is scale builds up in the tube, perhaps it sheds off, it comes down the downcomers or catches in the risers, plugs up the tube, and it ends up with a tube failure. And a failure, not only are you losing efficiency, but you're also apt to end up blowing a tube, or in the worst case, if you have enough scale in the boiler low water cutoff might not work properly, and the boiler will run out of water. So you want to make certain that you're preventing scale in a boiler to prevent boiler tube failure or even worse. So the next thing we're going to talk about a little bit is terms of protecting protecting a boiler against scale is to talk about what are we going to test for in the boiler to protect against scale. And we're back to our ASME limits. Neighborhood of total alkalinity and activity of 7,000. And again, these are ASME guidelines, and many different waters and different limits for control. And these are only guidelines. I would say that most boilers operate more in the 3,000 to 5,000 conductivity range rather than 7,000. But it's all a function of the water. With excellent quality feed water, you might run a boiler conductivity at 800 or 1,000, depending upon the pressure, even lower. So in a particular case, we'd like to talk about ASME control and conductivity limits at 7,000 micromoles. And again, this is neutralized. We'll come back to this neutralized conductivity in a minute. And again, I'm just saying that these are guidelines, not necessarily applicable to every plant. The conductivity in the boiler, there's two different types of blowdown that can occur. There's surface blowdown, where a small amount of boiler water is drawn off the surface of the boiler, and it's either done continuously or intermittently. And this function of the surface blowdown is to control concentration of dissolved solids and provide the correct boiler water chemistry is done through the surface blowdown. Bottom blowdowns are where water is emptied from the mud drum or bottom of a fire tube boiler, and this is generally used to remove sludge or any old deposits that have settled down into the boiler. And that's where it's done to remove material from the bottom of the boiler, not suspended solids that are concentrating at the boiler surface, where the pure H2O is leaving the boiler and the many solids that are in the water concentrate at the boiler surface. And it's just a depiction of a surface blowdown line and a blowdown line to help understand that. I'd also talk about two types of surface blowdown briefly. On a manual surface blowdown, you open the valve and there's either a needle valve or an orifice plate that controls the flow of surface boiler water going to blowdown heat exchanger, ideally, where the heat's recovered. Manual blowdown, you open the valve and you adjust the needle valve, or you have a continuous flow through a surface plate which is inside of a union. And you open and close the entire valve to control surface blowdown to maintain conductivity. Now the same drawing setup using automatic boiler blowdown controls, and what it does is you've still got a restrict valve as an orifice plate or needle valve, but prior to it you've got a sensor and controlled operating valve, either a solenoid valve or a motorized ball valve, which opens and closes based on what a sensor sends to the automatic boiler blowdown control. And on the conductivity that the sensor detects, the valve opens and closes, maintaining a very even conductivity level in a boiler. And this is a drawing of how that auto blowdown control might be a surface blowdown line. You've got water coming off the surface of the blowdown, and you've got a motorized or solenoid valve which opens and closes, controlling the amount of blowdown which goes to the drain. When you're doing that, it's important to remember that the automatic boiler blowdown control sensor does neutralize a boiler sample, and you may have to determine whether you're going to control unneutralized or neutralized boiler water using automatic boiler blowdown control. And this is a very basic water flow diagram for automatic surface blowdown control, and very closely follow the automatic boiler blowdown control installation recommendations. These controllers have gotten better as they have open, hold, and sense them now, which prevent the flashing that used to occur on these types of controllers in previous generations. I want to move on and at least say that it's very important to keep your boilers operating efficiently, and that you want to make sure that you don't have soot building up on a boiler, and you want to make sure your boilers are tuned up very important of a water treatment program, but not really a water treatment program, but it's an important part of a boiler maintenance program that you should be aware of, and I'm sure you are. Let's talk briefly about chemical feed of controlling scale. In the olden days, someone figured out that if you put potatoes into a boiler, the organics in those potatoes will minimize the amount of hard scale that forms in a boiler. This is pre-polymer technology, and even today, which come from trees are used to control boilage at the same time. But now we're not using so much of the potatoes in our boiler chemicals that we provide. We're using sludge control chemicals that are generally or polymers or copolymers or terpolymers, and every water treatment is going to have a little bit different blend, and depending upon the water characteristics, different blends are better for different water characteristics. And what these control chemicals do, they alter the physical structure of the solids that get inside the boiler that would normally form scale, and it can disperse, suspended, so they don't drop out and form scale. So small amounts of hardness and iron can't get into the boiler either from your feed water train or from your condensate system, which might have some corrosion in it. Get into the boiler, and what they do is they allow the crystals to form in a boiler. This is a photograph of a calcium carbonate crystal, and you can see that it's got very sharp edges and it's very specifically aligned. Now, what happens in a boiler is that once these crystals start to form and build up, you'll that the crystals line up, and it's very easy for more crystals to form. It's like rock candy when you're a kid. You'd hang a string in a solution of sugar water, and nothing would happen on that string for what seemed like days. But when you've got that string hanging in the supersaturated sugar water, after a period of time, the crystals start to build up, and once they're aligned, your sugar water becomes rock candy very quickly, and the rock candy forms quickly. So what sludge conditioners do is they take those sharp crystals and they form them into a soft sludge material that will not stick to boiler tubes. It can be removed either through surface blowdown or bottom blowdown. Now, we maintain the residual of polymer or phosphonate or sludge conditioner in the boiler. There's different tests that you can use, and because one has a little bit different blend of chemicals, there's different tests that are going to be used and different types that are going to be recommended. There's colorimetric and photometric testing that can be done to determine the amount of polymer in the boiler. The test that can be done to determine what to minimize the amount of scale that builds up in the boiler is to maintain an OH alkalinity boiler of over 200 parts per million. This drives the polymer hardness iron reactions to where we want them to be. And it's important to maintain OH alkalinity in the boiler. And in lower pressure boilers, higher OH alkalinity is generally not a problem, but actually preferred. Again, having the OH alkalinity drives the crystalline formation away from sharp edges to round ones. With dosing pump, you can see that with the dosing pump, you're able to control the amount of inhibitor sludge conditioner in a boiler at a very even level rather than over under the amount of residual of sludge conditioner you want in the boiler. Now, there are upsets in the boiler. How you might detect boiler water upset by looking at the boiler water tests that we'll talk about in a minute. And if all of a sudden your OH alkalinity drops off, you might have hardness or iron problem in the boiler. Or you've got boiler water which suddenly looks milky, and in a clear beaker, you end up with sludge that settles into the bottom of the beaker. You probably have another problem, oftentimes a hardness breakthrough that comes into the boiler. So that is a very, very overview of what a sludge conditioner does and how to test for it and what to look for in problems. But where you feed the sludge conditioner, ideally you feed a sludge conditioner to the feed water line. If you must, you can feed it to the deaerator, or you can feed it to the boiler itself. So what really to be done to prevent scale is to maintain your feed water quality as close as you can to those ASME guidelines. Try to minimize the amount of iron that's going into the boiler. Iron is a binder. It glues everything together. Maintain your conductivity limits within the specifics for your plant. Keep your OH alkalinity up and in limits, and maintain your sludge conditioner, and be on the lookout for upsets. So made steam in the boiler, the steam has gone out. We've got a concern about the condensate and protecting the condensate system. So worry about protecting the condensate system because a certain amount of alkalinity enters the boiler in the feed water and makeup. We talked about the ideal pH of your feed water between 8.3 and 10, and in that water there's carbonate and bicarbonate alkalinity. We add heat to the water. The alkalinity now breaks down to form water, which is H2O, obviously. That's a liquid that stays in the system or leaves as steam. Or it breaks down to be carbon dioxide, which is a gas. It leaves with the steam, and when it's released into steam, it goes into the steam system. And when the steam condenses, the carbon dioxide combines with the condensate, and it forms carbonic acid. And untreated carbonic acid will cause corrosion in your condensate system from the fact that it's acidic. Carbonic acid is acidic. There's a multitude of different amines that are used to protect the condensate system, which are neutralizing amines. I've listed them here. Your water treatment professional can direct you to which amine is best for your particular system. They have different characteristics. Some carry a short distance, some will carry a long distance to protect the far reaches of a condensate system. So there's many combinations